The last big topic of this week is Euler equation. I know we have already seen the Euler formula and the Euler method, and this is another thing that depends on Euler. Euler was pretty much the person that built this whole field of mathematics. So at the beginning into this field, there are a lot of things that depend on him and have his name. But let's go into it. We're looking at a special case of a second order linear ODE with non-constant coefficients, homogeneous, and we're asking ourselves what happened at around x naught when x naught is a singular point. So previously we have used power series to solve this type of equations when x naught is not a singular point. Now we're expecting it to be a singular point. So we're going to start by looking at a specific version of this second order linear non-constant coefficient homogeneous ODE. So now it's a handful. We're going to look at the Euler equation. This has a very specific format. X squared y second plus alpha x y prime plus beta y equal to 0. And you notice that x equal to 0 is a singular point. Can we solve this equation either way? We're focusing on this one because it's going to help us understand how it works in a more general case. So let's try to solve it in this tame case and see how we can get to a solution. If we are squinting at the Euler equation, you might notice that the zeroth derivative of y has no coefficient in x. The first derivative has 1 and has a coefficient that depends on x on order 1. And the second derivative of y has a coefficient of x that is x to the power 2. So if you're thinking of y as a polynomial, something like x to the power r, then the first derivative is x to the power r minus 1. The second derivative is something times x to the power r minus 2. And with the multiplications that we have in the ODE, at least the order is correct. They have the same power of x. If you look at beta phi, beta times x to the r, alpha x, x to the r minus 1, x squared, x to the r minus 2 have all the same powers. So maybe if we approach this equation, this Euler equation, by just assuming that x has this form, we'll be able to find the powers of x. This is similar to the assumption we did when we were building the characteristic equation. For the characteristic equation, we knew that ODEs often have exponential solutions, and we tried to plug it in. Here we look at the specific format, and we think that a polynomial would work, and we try to find the power of the polynomial. So we replace y second, y prime, and y by, respectively, r times r minus 1 times x to the power r minus 2, r times x to the power r minus 1, and x to the r. And you see that the powers match nicely. So if we assume x different than 0, can we really do that? Because we want things around 0. We do it anyway. If we assume x different than 0, we can simplify all these coefficients in x and have something that only depends on r. We have r times r minus 1 plus alpha r plus beta equal to 0. This is very similar to the characteristic equation, just a mild difference on the first term. But now we can solve it explicitly. We have that r is the solution of a second order equation, algebraic, no ODE. So we have an explicit formula for it. I'm not going to read it out loud, but we should be able to solve parabolic equations very easily. And we look at what happens in the standard three cases that we have already discussed for the characteristic equation. So we have what happens when we have real distinct roots, what happens when we have real roots but only one, and what happens when we have complex distinct roots. So let's start by case one. What happens when we have real distinct roots? Well, that means that our delta of the parabolic equation, that is alpha minus 1 at the power 2 minus 4 beta, is positive. So we have a value of R1 and a value of R2. We have that Y1 equal x to the power R1 and Y2 x to the power R2 are both solutions of our ODE. Let's check the Wronskian to be sure that they are independent. And remembering that R1 and R2 are different and that x is, we're assuming, positive, we do find the Wronskian is different than 0. So x to the power r plus 1 and x to the power r plus 2 with R1 and R2 different are a fundamental set of solutions. They're linearly independent from each other. But R might have even like square roots in there. What happens when you write x to the power r and r is not a rational? R is not a fraction. Can we still compute this? Turns out that for R rational, that you can write as R belonging to this Q with a bar, we can say that x to the power r is equal to exponential of r times logarithm of x. For R not rational, we use this property of the exponential as the definition of x to the power r. So we don't have to care about r being rational or not. We still have a way of computing x to the power r for any value of r. Let's look at an example of what happens when we have this situation in which our equation on the power of x has two distinct roots. So let's look at this case of the Euler equation. We have x squared y second plus 5x y prime minus 9 over 4 y equal to 0. And we're looking at a situation in which we want to solve around x equal to 0, but we're looking at x positive. We assume that yx is equal to x to the r. Then we can write the formula for r, that is r times r minus 1 plus 5 to the times r minus 9 divided by 4 equal to 0. We rotate things around. We have r squared plus 4r minus 9 divided by 4 equals 0. So we have a formula for r that is minus 4 plus or minus square root of 16 plus 9, all of this divided by 2. We simplify, that is minus 4 plus or minus 5, all of this divided by 2. That gives us either minus 9 divided by 2 or 1/2. So we can write that the general solution for this situation is c1 x to the power 9 divided by 2 plus c2 x to the power 1/2 for x positive.